All right, welcome everybody. Good evening to the what's usually the last TWed of the term. It's the spring 2019 TWed Lightning Talks. Woo! All right. A couple pieces of logistics. We are recording this and streaming this for posterity, and actually people find this stuff and because we record via YouTube Live, which is part of Google, and because I put in lots of useful tags on these videos, they get found and they get sometimes used as references, so it's pretty cool. But we are going out live, and the basic idea of Lightning Talks for the none of you who have never done this before is it's 2 minutes, it's no notes, it's just get up and talk. It's a friendly audience. Everybody should welcome the talks with the same enthusiasm that you expect your talk to be welcomed and thanked. So we want to hear lots of applause when each speaker finishes up. It's kind of a small crowd. We might have people that are coming in a little bit late. We've got one remote person, Anirudh, who I hope has a good excuse. And unfortunately, the projectors fries people's eyes, so I'm not bothering with the projector. But I've got his, I've got the audio turned up to 11 because I'm Linux, and so you'll be able to hear him everywhere. All right. So without further ado, Robin, make it happen. Thank you.
Hi, I'm Robin, working with Professor McInnes. So today I want to talk about the work I've been doing since last fall, where I did my co-op at a web product company in California. So what they do is they script the whole internet, especially the web pages, using computer vision. So how the cool thing about it is they would consider each HTML page similar to a picture, and they have their specific template using reinforcement learning to turn like each single web page they crowd into JSON. So the ambitious goal of the work is we have a dump of like all the active listed e-commerce products over like hundreds of e-commerce sites during last year. That's probably a total of 2 million product instances from the internet. So we want to see whether it's possible to build a consensus like product catalog ontology from it. So the available information is like, usually when you go to a product instance page, like on Amazon or on eBay, you usually have a breadcrumb, which is usually the secondary navigation probably on top of the website, where you can have a sense of your location or position of this product within its own like product ontology. One example would be like from home like electronics, cell phones, and iPhone like 64 gigabyte unlocked with a color attached. So what I did is I built a like autoencoder, which tried to encode the JSON information of each product instance page. And based on the encoded representation, I do like instance level similarity matching so that I can identify the same or very similar product instance, which is listed on different e-commerce sites. So based on this kind of hierarchical clustering of the instance products, we will have a way to merge all these like different product catalogs among different e-commerce sites, so that we can finally have a merged product catalog tree, which is like more comprehensive and complete than one individual product catalog from one specific e-commerce site. So that's the research problem I've been working on.
All right, thank you, Brian. Yeah. If only there was a way to embed RDF in web pages. All right. Yeah. Wouldn't that be something?
Come up with that idea.
Well, you could call it like, you could associate with attributes.
Oh, that would
No, that'd be
that would
crazy.
useful.
Yeah, yeah. We could call it attribute RDO.
John may have had too much caffeine. So, here to mention one thing briefly. So I spent a lot of my time this last semester working on building websites for the new Rare Center here at RPI. So I just kind of want to throw that out there. If anybody else happens to be building websites for the Institute, please come see me. I have lots of pointers to improve the project. But so my research has been around the census of deep life. They would like to do a mapping project for their website as the Deep Carbon Observatory is coming to the end of its life. And so anyway, so what I've been doing is working with raster files, particularly mapping the chlorophyll, isotherms, which are the temperature beneath the surface at a particular depth, the sediment thickness, and the age, the measured age. So it's mapping those raster files onto a world map and then being able to select those as layers. And then projecting other information on top of them from, they want to be able to actually, whatever data set they want information on, or if they want a visualization of, they want the application to actually be able to then project that on top of whichever one of those layers or the combination of those layers. So I don't know exactly where that's going to land, but we're hoping to get that finished before the end of the year. So.
This is the big legacy.
Legacy, DCO legacy.
Yeah,
There it
legacy.
is. Up next. Iron.
Oh, yeah, so I would go right ahead.
Okay, thank you. And thanks, Brenda, for the segue. So hi, everyone. My name is Anirudh Prabhu, and I'm actually going to talk to you about a DCO data legacy that we created called GEMI, or Global Earth Mineral Inventory. If you've talked to me at all in the hallway or seen some of my previous talks, I'll constantly be talking about this project called DTDI that we've been working on, Deep Time Data Infrastructure, which involves a lot of mineral data, fossil data, and we've been creating networks and writing papers on these things. So along the lines, as we were successfully publishing papers using this data, particularly the mineral data, we noticed that there are some well-established data resources for getting mineral data and the various geological, biological, and chemical parameters, but they're fairly segmented. And even so, that a lot of the data is like in non-digitized form, like in the Handbook of Mineralogy. Other data is available in RUF, in MINDAT, and what's called ODR, or Open Data Repository. So there was a need to really assimilate all this data and merge it into one resource under a single information model, and then build some sort of accessible interface on top of that so that the data can be retrieved easily and can be used. And just the amount of data that you want for your analysis you can use, and you don't need to download the entire data dump every single time. To solve basically this problem and to sort of propagate these kind of, this information model to the rest of the community, we built the GEMI information model. And so that's the basis, the crux of our, the paper that we've been writing. So in development is a paper that I'm the data lead on that we're writing, which is due at the end of this month. So that involves multiple things. So it's a data paper where we are developing, assimilating the data sets, developing an information model, using the information model to put together this interface based off of the current DCO data portal. And we also have a citation policy and evaluation metrics that we've listed down for a data legacy or a data resource in general. So that's the thing I want to talk to you about. Thank you.
Cool. So, Anirudh, can you advertise your talk in 2 weeks?
Yes, actually, the talk is exactly on this topic because I would just have finished and submitted this paper. So I wanted to highlight that in the talk 2 weeks from now. It's the GEMI DCO data legacy that I'll be presenting on.
Awesome. Really looking forward to it.
Yep.
All right, here.
Hi, everyone.
I'm Sabir. I'll be talking about abductive reasoning over health data. So just to understand abductive reasoning, real quick, deductive reasoning is kind of reasoning in the form of horn clauses, so if-then statements. So kind of in the semantic web context, if you have a set of triples in a graph, then based on a rule, you can infer a set of new facts, right? So the abductive reasoning is kind of going the other direction, where if you have a set of facts in the graph, we want to know how they got there, right? Are there rules that would result in that fact being put in the graph? And if so, do the consequence, each clause of the rule, do they exist in the graph as well? And if so, that might be a possible explanation, right? So how do we do this in the context of health? Fortunately, a lot of work has been done in terms of creating ontologies and graphical representations for biomedical knowledge. And there's a collection of this work called the LSLOD cloud for life sciences linked open data, which contains databases like KEGG, CTD, UMLS, I think, is on there, Drug Bank, a bunch of them. So this work already exists, and a group in Stanford reduced the set of the size of the graph to be a lot more, I guess, usable in the system called Allegra. So that's kind of like my starting knowledge graph. And the idea is, given this, can we find protein-protein interactions or protein-drug interactions that might help explain things like patient adverse drug reactions.
All right. Thank you, sir. Is this your phone? No. Yeah. Is that your phone?
It's okay. I'm glad to not have it very much.
All right. Thank you. Hi, my name is Ahmed Elish. I work with Professor Fox, and the project I want to talk to you about is called Lake AI. We're taking an AI approach to studying lakes and the water quality and different aspects of the watershed around the lake using remote sensing from satellite imagery. So we have a data set of around 1,000 lakes in their images, as well as in situ measurements taken at these lakes relating to water quality and water clarity and a bunch of other measures that have to do with the biology of the lake and so on. So what we're trying to do is analyze these images and see if we can relate what we've learned from the images, the features, to these measurements taken from the lake. Our initial approach was to use deep learning. We tried to use models, autoencoder models and convolutional neural networks to try to learn features from the image and then try to relate those back, find the relationship between them and the quality measurements. But that approach didn't do so well. We weren't able to learn interesting features, mainly because we have varied sizes of the watersheds and the images themselves, including the spatial configuration of what is in the image. It varies greatly more than, for example, people's faces or animals and such. And so we decided to take a different approach, an unsupervised approach to superpixel segmentation. Superpixels are groups of pixels that are relatively close in proximity and encode the area from which they are, of the image that they come from. And so they're a good measure of what is going on within the image. The approach we're using is hierarchical clustering. We start by putting each pixel in the entire image in its own cluster and iteratively build and narrow down by increasing the number of clusters until we get to a point where we have good segmentation of the image. We want to then take that as a starting point, because then each superpixel will be a patch of land and or water and so on, and will reflect a certain part of a certain geographical feature. We want to then take these segments for each image, sort of do clustering to find how many types of segments there are per image, and then the hope is to take that and run the same exercise for the entire data set, for the 1,000 lakes, and sort of have clusters of clusters, which we can then, for example, compare to the USGS land cover database, which classifies each pixel in an image as belonging to a particular land cover class, so vegetation, for example, water, and so on. And so the idea is then to take what we've learned from the entire data set and again try to relate them back to the measurements in an effort to try to perhaps predict what goes on and what will go on in the lake or in the environment surrounding the lake based on just what we see from satellite imagery. And the point is to predict things like algal blooms and so on. So it's sort of an environmental, the objective is an environmental study. Thank you.
All right, thank you. Super pixel.
Hello, I'm Neka. I'm a student of Jim Handler, and I'm here to talk on my independent study work with Professor Ping-Kun Yan in the biomedical engineering department. So we're working on automated image description as such. So what that means is giving a medical image, we want to be able to describe the content of the image and also be able to engage a physician in some form of dialogue with the image, so in form of question answering. And so in order to enable that, we started image captioning. And so we're currently using the simple vanilla image Google show and tell, but we've also been doing extensive literature review, and the most prominent research is top-down, bottom-up attention model, which tries to combine both the features obtained from both the attention obtained from just scanning through the convolutional neural network, and also the features obtained if we attempt to get the model to first identify the objects without knowing the question or the context of the image. So the hypothesis is if we combine both the top-down model, where we look at every single pixel and use the information there to generate the next word, and combine it with knowledge of all the objects that are currently within the image, we'll be able to generate better captions. And when we generate the caption, the next step is to be able to answer questions. So for that, we'll probably need physicians to give sample questions they will ask on an X-ray image. We are currently working with OpenEye's data set, which has a little over 7,500 images, and that's just because I'm running it on my system and I do not want to go higher. But there's a Stanford data set that has 300,000 X-ray images. So once we get a model that we're optimistic about, we'll move to the bigger data set to see if it improves the performance.
Right. Run that on the cluster.
I kept running into errors with the idea of cluster, so
Well,
I just gave up.
What did you talk about?
Yeah, I think Oshani said it was because who was running his own.
We've got a way to moderate that stuff. ASCII. Yeah.
Hello everyone, I am Neha Keshan and I am Professor McInnes student, and I'm going to talk about the nanomine and the metamine work that we are doing in the lab. So it's in the polymer nanocomposite field where people are trying to understand the relationship between the properties and the design, how they connect and how they can create new designs and use them for new applications which are complex. So we are trying. So Jim McCusker has already built the initial framework using the WEDS, where we have this beautiful visualization where they can go and play and see what are the current structures already there and how they can work with it. And we're using the WEDS in-house platform for it. And so my work this whole semester has been to understand the WEDS platform and get familiar with the whole nanomine work that is there, so that I can continue with the unit tests and also extend it to the metamine ontology, where we have more various material terms, which I'm not that familiar with now. But yeah, that is what we are working on. Thank you.
All right. What's that?
Hi, everyone. My name is Yarden, and I am a master's student of Deb McGinnis's. So this past semester, I wrote and defended my master's thesis, which was a feature assessment. It was a feature assessment model for data portal evaluation. So I looked at different data portals in both the government public sector information and scientific data portals, specifically biomedical data portals. And I was basically trying to understand what they do well, what they are lacking, and what kind of metrics we can define for them in order to be able to compare and contrast how these data portals are effective in what they do. So I developed kind of a metric scheme for how to rate these data portals. So I developed 3 categories, so technical features, semantic features, and reuse features, and basically looked at each of the 6 portals that I selected and gave them a rating from 1 to 3, where 3 meant that they had the feature, they did it well, they used it non-trivially, and 1 meant that I couldn't find any significant use of that feature. And based on the results that I got from all of those features, I created 7 recommendations that fell along the lines of things like leveraging semantic data, having a public API and Sparkle endpoint, documentation, and using open source software. So based on that, I am looking to take that work and kind of scale it down into a journal paper with the help of both Deb and Jim Hendler, and just kind of tighten up the analysis a bit and do that. So thank you.
Thank you.
Yeah, I couldn't tell if it was me or not.
Sorry.
That's okay. Hi, everyone. My name is Kevin Blissett. I'm a student of Hung-Ji's, and I'm going to kind of ambitiously try and do 2 things in a 2-minute talk. So I'll talk a little bit about my work and then share a lesson learned. My work this semester has been based on, in our lab, we're interested in name tagging. So we want to get unstructured natural language, and we want to find all of the names of it. And that helps us understand the important people, places, things that are talked about in that document. But the tricky thing is we'd love to do it for languages we've never seen before. You know, like small languages in Africa or the Middle East or something. And, you know, that sounds like a really big problem, but it turns out if you give human beings those documents in a language they've never seen, along with a little bit of parallel data, humans can actually do a pretty good job of doing name tagging for languages they don't know. So I've been working on building a model to have that same intuition. And the way they do it is we have a natural intuition about when things kind of look the same. That's hard to capture with a metric like edit distance or something, but hopefully you can build a model that captures the same kind of idea that says, oh, these names, even though they're in different languages, kind of look the same. So that's my work. And as I was working on building this model, I was training my models and working with a lot of data, and they were performing really erratically. And you know, my learning curves were very strange, and they didn't behave the way I thought they should. And I really struggled with it for a long time. And eventually I decided to go back to basics. And rather than taking my whole data set, I wanted to scale down and use just a small part of it. And the lesson I learned is that when I used just a small part, suddenly sanity returned and everything behaved the way I thought. And then as I slowly scaled up from there, performance went the way I thought. So my advice is, we're people who love data, and we always want more data, and there's never enough, and we want to use everything we have. But sometimes the best way to make progress is to take a step back and to start small. Thanks.
All right. Thank you. Two lightning talks in one. Let's jump ahead to 50.
My name is Fei Pan. I am a 3rd year PhD under Professor Peter Fox, and this semester I'm majorly working on 2 projects. One is the one that is part of the project Andrew mentioned, the DTDI, Deep Time Data Infrastructure. So we are trying to use the cell parameters to predict the composition of a mineral. And Shauna, who's the collaborator from Carnegie Institution, she has been setting up more restricts about how we're gonna formulate the algorithm, and adding more features and including more minerals. Also, we moved from Earth mineral to Martian mineral, which are so the Earth mineral are from ROF data set I think I mentioned before, and the Martian data are from NASA. They have these Curiosity rovers on the Mars and collecting data. So we are preparing the submission and probably going to wrap it up next week when Shauna visit. And the other project is my potential thesis topic is the taxonomy induction using embedding. So basically idea is to use as much existing ontologies or taxonomies as possible and try to append more information from there.
All right. Thank you.
Hi, my name is Shweta. I am a student under Professor Fox, and I'll be talking about my independent study work. I'm doing it with Professor David Mendoza in Industrial and System Engineering. We are trying to work on a simulation that he had created. It's an experiment which works basically with mainly with the emergency response teams and how they actually respond to a specific emergency situation, given the training they already have, plus how they actually process the information that they are receiving at that particular moment. It goes into the field of cognitive science, where we are trying to also see how divergent thinking and convergent thinking comes into picture. And this simulation was carried out where it was a conversation as well as they had a UI on which they were conducting this experiment. So we have huge data sets which were actually conversations that were transcribed. And using these particular data sets, we are trying to find the correlations, how the decisions were made, what is affecting the decisions majorly, and the very biggest question we are trying to answer is how are decisions made? What are the human cognitive factors that are getting that play the biggest role in actually making a decision? That's it. Thank you.
I'm Jim McCusker, and I sprang this on John at the very last minute. I wasn't sure if I had something for you guys, but I do.
You have something.
Yeah, why not? Okay, so
I'll do one.
great. Okay, so
I'll use up the remaining time.
if I told you guys you had 2 years to run a marathon, how many of you are terrified by that thought?
2 years.
You
will be running one.
Yes, you'll be running one in 2 years.
Not you can take 2 years to run.
Yeah. No. 2 years to train for a
Get
marathon.
you.
Okay.
Get your ontology.
Yeah. So anyway, okay. So that sounds less appealing.
Probably waste a year.
Well, yeah, probably. Well, so here's the thing. So the average PhD takes 5 to 6 years, right? And takes at least 20 hours a week of really dedicated time. At least should be. So that's about how long I took on my PhD. It took me 2 years and between 3 to 6 hours a week of work to train for a marathon, going from nothing to finishing a marathon in 4 hours, 38 minutes. What you're doing now is harder than training for a marathon. And I want to put that into perspective for you guys. The other thing is that there's some lessons that I learned from training for both, for training for a PhD, training for a marathon. The first one is that building in exercise into your daily routine as a PhD student will give you more energy than it will take from you. You put in, say, 4 hours a week of exercise. You exercise for an hour a day, 4 days a week, or as I do it, 2 hours twice, and then 1 hour twice, and then 2 hours on the weekends. You see me, I'm like going nonstop. I'm like John now. I was not like this when I was actually a grad student. I was a lot less energetic, but once I started it, it was like a whole thing.
You and Dominic.
Yeah, Dominic, another student. He's now running. He ran a half marathon, and he's just like doing everything. He actually just got an assistant professorship. But the cool thing is that it won't take time away from your day. It'll actually give you more energy to get stuff done throughout the day. And you won't be sitting there thinking, oh God, oh God, oh God. Which I know you do because I do.
Running up the street.
Yeah, yeah, that's the thing. Well, but the first 6 months, you'll be, why am I doing this? But But once you get past that, you're going to actually look forward to your runs and want to and use it to clear your head. The other thing that I wanted to talk about that I learned from this, and I had to learn it the hard way from both disciplines. There's a phrase from that the Army uses called slow is smooth, smooth is fast. This isn't an equation. It's obviously not, because it's contradictory. But it's a progression. And you see it if you learn karate. This is how they teach you karate. If you learn a musical instrument, this is how they teach you to play an instrument. If you do anything where there's a skill that you're building up over time, if you do something slowly and carefully and consciously and build up that skill that way and not rush into it and assume you can just kind of blast through it, you'll build up the ability to do it smoothly and carefully. And once you do it smoothly and carefully, you can then execute it fast once it's actually in there. And once I started applying that to my running, I actually took almost an hour off my marathon time. It was really amazing. When I started applying it to my research and software development, I started going from getting answers that I could get to work to knowing that answers were right, because I was able to do the research and actually get through things and understand it from the ground up. And so really from both sides, slow down to go faster is really going to help you in both cases. Don't worry about how long it takes you today, because you're in this for the long haul. You've got 6 years. Not everyone has 6 years left, but you've got, this is a long process. This is how long it would take to train for a 100-miler, not for a marathon. And you have to, we have the saying called eating the elephant. How do you eat an elephant? You eat it one bite at a time. Yeah, you just take it a little bit at a time, and you get it done.
There's also boiling frogs.
Well,
that's a whole other.
That's a whole other thing that has to do with. Yeah, but it is relevant to a PhD.
Yeah. That's
Okay. So anyway, I think that's all I have. But
all right. Thank you. Thank you.
Oh, the last one.
Yeah. Oh no, go right ahead.
So I'm Jason Liang, Zhisheng Liang, my Chinese name. So I'm a PhD student, supervised by Professor Darryl McGinnis. So I have been working on my research for this semester, and I just gave a presentation on this Monday. So it's mainly about a literature-based survey on knowledge graph embedding. So knowledge graph has been very popular in recent years to support a large number of applications. So because knowledge graph is actually a symbolic net logical system, so when it become larger and larger, so for example, Wikipedia now has like millions of entities and billions of triples. So when the scales comes up, it's become more and more difficult to manipulate it. So what people propose to solve this problem is to learn low dimensional representations for the entities and relations in the KG. So in that way, you can transfer this kind of symbolic operation into some algebra operation. So you can, with the learned embeddings for the entities and relation, you can actually perform the tasks like link prediction or invariate the true value of a specific triple. And then you can also support a lot downstream application like information extraction, where you want to extract the entities and the corresponding relation from a natural language sentence, or you might want to do a question answering system over knowledge graph, which can be provide user with natural language query interface for the KG, and then which is what really interests me is that people is also trying to incorporate the test resources from the large test corpora like Wikipedia to enhance the quality of the learned KG embeddings. What they did is that they first aligned the triples from Wikipedia with the natural language sentence in the Wikipedia using some anchor links or using some existing anti-linking system so that they can embed some of the KG concepts into back into the natural language sentence so that you can use some existing natural language word embedding techniques like word-to-vec to change the embeddings for the words and entities and relation in the John continuous vector space. So, and another word that is also interests me is that when we do the KG embedding learning, how can we incorporate some existing human knowledge, like some logical rules, which means that you can say we know the rules like is father of is equivalent to 2x father of relation to be concatenated. So how can we encode such information when we are doing the KG embedding learning? So what they did is that they formalized this problem into optimization problem called integer linear programming, in which that they make those logical rules. They transform those logical rules into constraints of this kind of optimization problem and solve the problem, so that in the learn embedding the constraints will hold, and then they can also like encode the global information from the original the KG graph into this kind of embedding, and then so that the embedding quality will be improved somehow. So this is I think the one promising direction is that for us to explore how can we use this kind of learn embeddings, KG embeddings in downstream applications such as the IE system and the QA system and other some kind of rule mining system. So that is what I've been done. I've been doing this semester. So.
All right, thank you. All right, I guess I'll go. Well, first of all, thank you everybody for this, and we'll wrap it up at the end. So, what do you want to hear about? Do you want to hear about brewing? Brewing.
Yes.
Brewing, or do you want to hear about boat building?
Oh, I was hear about your
Or you can hear about
Just one.
websites.
How about drinking your beer on your boat?
Yes. Yeah.
Brewing on
So imagine. Okay. So imagine. Well.
So I know about RDF encoding that allows you to work your way up through a brewery, right? So,
okay. So I'll tell you about. So I've got a lot. So my brain works a lot like what. It's kind of going the same direction as Jim's message. Okay. There's a lot of diverse interests go into this, and I think. There's the physical side. I mean, I don't get this by sitting around on the couch, but also mentally, having a lot of different interests. I think I was 30 when I started my PhD work at Dartmouth 100 years ago. So do the math on that. And when I started my PhD work, I had my eldest daughter, who now has a PhD in math. Was just starting kindergarten, and my youngest daughter was like 2 years old. And in the same way that getting the physical exercise is a great diversion and keeps you, although I had to throttle back, I was racing at the time. It's hard to do the racing and do everything else. But having the family and having this kind of this project that it has this way of putting a kind of constraint on you and order on you that just kind of goes through. Also, since I've worked for 8 years in digital equipment prior to that, I felt I had like this unfair advantage because I could do my PhD work as if it was, just another job, which works out. But anyway, a couple of my interests that I picked up, for years, for most of the 2000s, I've been boat building. Okay, and I built different kinds of boats. I built replica mahogany runabouts that look like boats from the 1930s to classic rowing boats. And I'm about 2 years into a tugboat right now, a wooden tugboat, which hopefully will flip this summer. You build it upside down first, right? You build the hull, and then you got to flip it over. And we think it's gonna be electric powered. It was gonna be a diesel, but electric power has become affordable enough that it's actually practical for a weenie like me to do that. And we will be drinking, imbibing sporty beverages on this boat because, most people have party boats that are pontoon boats or whatever. I can't have that if I'm a boat builder. So what kind of a boat am I going to build? A little tube go around the lake. So, anyways, you guys will see pictures of that. There was one project that I wanted to share with you. I've been mentoring a group of students for most of the year, starting in the fall, on a project that we call Twitter Time Machine. Okay, on a campfire. It's a campfire visualization that uses I think most of you know what the campfire is, right? I've been blabbing about it enough, and many of you have seen demos, but we call it 2.5D because it's got a floor, but it's coupled with that, we've got this wall that's about 8 foot in diameter, about 2 foot high, and you have these integrated visualizations. But based on a coding style that we created here at RPI called Multi-Window Shiny, we're actually able to have these visualizations synchronized based on the R platform. So these can be live visualizations, but also based on the Multi-Window Shiny technology, we can also have other screens available. So you can have a laptop that's an interface. You can have your interface, your visualizations on the floor and the wall, and you can have other monitors. Some of you were at Hannah De Los Santos' talk, our Pirates talk last week or the week before, where she talked about that. She's going to be presenting at the Worldwide R Users Group this summer in France. Her R Multi-Window Shiny, which is really awesome, is going to be an R package, so that's really cool. And I think it'll be the first R package that comes out. So what Twitter Time Machine, in short, the students are replicating this work called Beyond the Hashtags. It's web science work, computational social science work that's trying to understand the sub-communities that have formed under the Black Lives Matter hashtag starting in 2014. So you can imagine, there's these different events that have happened in society, police shootings in particular, and then there's a flurry of activity on Twitter as a result of that. But and all under this Black Lives Matter hashtag, but it's not all from the same community. Black Lives Matter, that hashtag does not represent a unified community. And so what this work studied was for each period following some event, and there were nine that they studied from 2014 to 2016. Let's understand the subcommunities, apply network analysis to understand and characterize those subcommunities. But it's like artisanally crafted research. Okay, you're identifying this, you're harvesting the tweets for that, you're doing the network analysis for that, and it's a discursive analysis to try to understand what actually does this group represent. Oh, it's a bunch of conservative newscasters that are tweeting content, or it's young black Twitter, or it's activists, or it's liberal media. Okay, so and it changes from this period to this period. So prompted by Brooke Foucault-Wells, who I think you heard talk this term, visiting scientist from Northeastern, she's been coaching us the whole year. Let's try to create this immersive, interactive tool that visualizes co-occurring networks on the floor. So shared hash. So first, let's replicate TweetDeck around the wall. Different columns representing groups of users that characterize the groups. Let's show networking on the floor that shows shared hashtags, mentions, retweets, shared content. So we got 4 layers of networking on the floor showing the relationships between these. Let's make it interactive so we can define a new, maybe put this user over here, have a new column representing a new thing and see how that relates to the others. Let's put statistics on these big monitors while all this is going. Let's click onto that link in that column and put it up here. So these students have been working on this. And it's amazing, it's taken 2 terms, but they're finally getting it all pieced together. And it's been a lot more complicated than everybody thought, but it's pretty cool. And we've got a lot of not complicated campfire work that's coming up this summer. Jim, there's going to be a return to some government data, linked open data demos that are going to be done. We just got a panoramic 360 camera, and Eric Amaris and I did the first demo on the campfire that uses 360 video on the campfire. It's pretty cool. And we'll have somebody playing with that this summer. So a lot of cool things to report throughout the summer and going into the fall. So that's my 2 minutes. You want to know about the brewing, you can ask me at any time. I've got I'm halfway through a maple sap IPA, West Coast IPA. That's like Green Flash. If you remember Green Flash down at Finbar's, it's a clone of.
By the end of the semester.
Yeah. What's that?
Will it be done by the end of the
It'll be done next week, or it'll be done by Friday, a week from Friday. So thank you so much. I want to reinforce that Anirudh is talking 2 weeks. There's an Art Pirates next week that'll just kind of be a let's hang out, and do stuff. But that's it. So let's all thank you so much. All right. Have a great one.
And, hey, John,